everyone, and welcome to another episode of Echo Live, coming to you from the Michigan Science Center. My name is Anna, and we have a very exciting program planned for you today. Today, we're talking about electric motors. So keeping with the theme, since it is National Makers Week, we would like to talk to you a little bit more about how you can use these different engineering skills and trades in order to create or tinker with toys at home. So before we get started, if you haven't done so already, go ahead and introduce yourself in the chat feature of the program that you're watching on. I can see some familiar faces starting to chime in on our Facebook and on our YouTube page. So welcome everybody. Thanks so much for joining us for another exciting program. If this is your first time joining, using the chat feature is your way to interact with us throughout the program. You can ask questions about any of the experiments or demonstrations that we're showing you, but you can also answer questions that we ask of you as well. So we're talking about electric motors today. Now, we talked a little bit about mechanics yesterday in our tinkering program, where we talked about cardboard automata. So in our lesson yesterday, we built these cardboard automatas, and that activity guide is on the Michigan Science Center's website so that you can try this at home. Our friend Raul taught us how to make a kinetic sculpture, so a sculpture that moves, using some very basic principles like a cam system, which is represented over here on this far image, or a crank system, which is represented here in this yellow cardboard automata. In both of these automata, we turn some sort of wheel and axle system in order to cause our sculpture to move. But really the driving force behind these automata comes from you, the person who's operating the automata. Now, in most of our toys, right, we don't necessarily need to provide the force. That force is normally provided by some sort of electric motor. Now, we're going to talk a little bit more about how electric motors work, how they convert electrical energy, like from a battery, into kinetic energy, or the energy of motion or movement. So we've got a diagram here. So let's first talk about this stationary diagram before we move on to the next one. This breaks down the basic parts of any electric motor. We'll need a power supply. In this case, it's represented as a battery. A battery gives us direct current flowing from the negative terminal to the positive terminal of the battery. And then it's represented flowing around this circuit or the parts of this motor by these arrows. Now, this current will reach these brushes, or what we call this part of the motor we call the commutator. Now, as we send electricity through these wires, they cross a magnetic field. Now that's important because we need that interaction between our electric and our magnetic field, or our current and our magnetic field, in order to generate a force. So the force, or the rotation of this motor, is represented by this arrow on top. So when this current crosses our magnetic field, and magnetic fields flow from north ends of magnets to south ends of magnets, or poles, when those two interact, this coil will start to rotate clockwise. And let's see if my GIF will start up here. So we have a moving version of this diagram over here on the right. So let's take a look at how those forces interact. As our current crosses the wire, a force is generated, which causes the brushes and the wire to rotate around. So you can see that we're opening and closing the circuit. And once these brushes connect back to our wires or into our circuit, a force is generated over and over and over again, which causes this coil to spin continuously clockwise. So it does not change direction. It always rotates clockwise. Now, this direction is important, and we've talked a little bit about a rule already that could help us to understand the direction that results from the direction of the force that results from an electric motor. We talked about a right-hand rule in our electromagnetism episode, but when we're specifically talking about electric motors, we need to use our other hand and talk about Fleming's left-hand rule. Now we've got a diagram of a somewhat similar mechanism to our last slide. This is a very simple homopolar motor. And it has all of those same parts or same forces involved in this diagram as in our last one. We can also represent those on our fingers. So if we think back to how we used our right hand rule, we'll point our various fingers in various directions according to the rule to tell us the direction of the force. So our first finger, if you'd like to follow along, hold your hand in the same direction or the same shape as you see here on the screen. Our magnetic field flowing from north to south pole is represented by our first finger. So go ahead and point your first finger. And then current, which we said flows around our circuit there, is represented by your second finger. And these fingers are at 90-degree angles from each other. This is a three-dimensional graph here. So you can imagine that this arrow is almost coming out towards you into the slides or towards you from the slides. So we have magnetic field represented as our first finger, and then current represented as our second finger at a 90-degree angle. So when we have those two forces meeting each other, our thumb, if you stick it straight up, will give us the direction of the resulting force. So let's take a look at that up close. So if we have, I have some materials here, and we'll get to those in just a moment, but just like in that diagram, we have our field, our magnetic field as our first finger, current, which is my second finger, and I have them at 90-degree angles from each other. And this this left-hand rule works no matter which direction you point your fingers, so long as you always keep them at 90 degrees. So I could do it like this, where my second finger is pointing towards me. I can do it where my second finger is pointing up, where it's pointing to the side, or down so that we can see it. Now, once we have our fingers lined up in the place of how we see them in our diagram, we then stick our thumb up, and that gives us the direction of the force on the motor. So in this case, how my fingers are oriented, the force would be towards you. But if I turn my fingers, right, the direction of the force can change. So what's important is that your fingers don't move, but the orientation can. Now we've got an example of a simple motor right here on the table. And this is something that's very, very easy to recreate at home using just a couple materials, because we said all we need to create an electric motor is a power source like a AA battery. We need a magnetic field, which we're going to generate using these very, very strong neodymium magnets, and then something conductive to carry that charge through the circuit. And so for that, I have some aluminum soldering wire. Copper or aluminum are both great conductive wires for this experiment. Copper works best, but aluminum is a little bit less expensive and easier to come by. So let's take a look at these materials up close. And we'll give this activity a try here on Echo Live, but I've also pre-made some examples of homopolar motors, because this is one of those activities that takes a little bit of tinkering. If we remember back to that engineering design process or invention process that Raul talked to us about, we know that our steps aren't linear, that sometimes our first draft at an experiment or at an invention doesn't go as planned, but that's okay. That just means that you need to tweak it and then try again. Now, the most important thing, so we'll be building various shapes that we'll be putting onto our homopolar motor in order to get them to balance on there and rotate. So I have some examples here. And the most important thing is that whatever you create is able to make contact with both the top of your battery and the magnet that's going to sit underneath, just like in that diagram we saw, but it needs to be symmetrical or evenly weighted so that it doesn't fall off your battery. So you can really make this in whichever shape you like. Something simple that you can try is something like an M. So if we kind of spread our wire out here, remember always trying to keep it as symmetrical as possible. We can always tweak it later. So I've made somewhat of a heart or like an M shape on top. And we'll just go ahead and make sure that my battery just about fits inside this shape that we've created. So that looks pretty good. And then our wire will need to make contact with the magnet on the bottom if we want the electricity to flow. This is the trickiest part, and sometimes the easiest thing to do is to wrap it around something circular like your AA battery here. Pliers are super helpful for this type of experiment as well. Can be a little bit difficult to work with the wires without them, but it is possible. So we'll go ahead and give it a try here. We'll just bend our wires. Now we need to get them to line up or cross each other. And so this might take, again, some tinkering. And we'll be placing it on the top of our battery and then trying to get our battery and magnet system to turn into a motor. So I've just stuck my magnets here to this iron block so that it's not going to topple over once our motor starts to spin. But you'll notice that your battery sits really nice right there on top. Pretty good hold. Batteries are magnetic. And then we'll just go ahead and we're going to try to slide on our motor that we've built. And then this is the part where you need to make some adjustments. So you want to make sure that your wires are making contact with your batteries down there on the bottom, but that they're not too tight like mine are, that it's not going to allow your motor to rotate. So this takes some time and some tweaking, which is why I've come prepared with a couple examples, but you'll see that they all follow this same principle. So this one I built out of copper wire, which we said is a great conductor on previous episodes of Echo Live. And if we just go ahead and balance our wire right here on top, you can see that our motor starts to spin. And as it makes good contact with that magnet on the base, maybe we make one quick adjustment here, it will start to spin relatively quickly. Let's take a look. So very simple stuff, right? Only a few forces involved in creating this motor. As our magnetic field and our electric field from the battery cross each other, right? We generate that resulting force. The force is different on both sides, right? Because our electricity is flowing down and through the wires, but our magnetic field is also traveling from north to south pole. And so as those forces cross each other, we get a different resulting force on each side of the battery. You can imagine this like on this side of the battery, we can see that our wire is moving forward or towards the camera. So it might look something like this. But if we flip our hand around, the force looks more like this on the opposite side, just based on the direction of our current and of our magnetic field. Now we've got all sorts of examples here. So take our copper dancer off. We'll go ahead and try this one here, which I'm pretty proud of, but has some limited success with getting to move. We'll see, sometimes it needs just a little help. So this is made out of that aluminum soldering wire, which I had laying around, which is not as good of a conductor, unfortunately, which gets it a little bit, needs a little bit more. There we go. Oh, it wants to. Well, we'll keep tinkering with this. But in any electric motor, in any motor powered by electricity, we measure its speed. Oh, it would help if I didn't get that one stuck to these magnets. We measure its speed in rotations per minute, or RPM. See, that one, even though I've weighted it down since it's made out of copper wire, works extremely well. So we'll leave our battery dancer here just to keep spinning on just a little bit longer. And let's talk about how we measure the speed of these motors. So we call it rotations per minute, or RPM. And if we think about our cardboard automata, right, we're really limited to the number of rotations per minute that our hands can produce. I'd say based on the size of our automata and really just the maneuverability of our hands, that we could realistically get maybe 70 rotations per minute out of that cardboard automata. But that's why we create these electric motors or even combustion powered motors, so that we can get more rotations per minute or more RPM. So here's a moving diagram of what that would look like inside a car engine. So you can imagine that for every rotation of one of these pistons, right, that is 1 RPM, or 1 rotation per minute. Could you imagine if you had to turn your car by hand, right? That would be pretty crazy, because car engines rotate thousands of RPM, or thousands of rotations per minute, depending on what gear you're in or how fast you're going. But I have a fun quiz for us. Let's go ahead and let's take some guesses about which of these motorized devices has the highest RPM. Which of these 3 options do you think rotates the most times per second? Do you think it is this top blade of our helicopter, Is it the motor in our electric toothbrush? Or is it the wind-powered turbine? So take a minute, think about how fast you think these various objects are rotating, how many times per minute, and tell me which one do you think has the highest RPM? Go ahead and type it in the chat when you think you've got the answer. All right, some guesses starting to come in. We got a friend in Zoom who thinks it is the toothbrush for sure. Zara thinks maybe it's the windmills. All right. Oh, and so definitely people have great guesses. Lots of people voting for the toothbrush, lots of people voting for the helicopter. So maybe you've seen a helicopter up close, right? We know that those blades have to rotate fast enough in order to generate enough thrust that it will lift the helicopter off the ground, which must be pretty fast. Maybe if you own an electric toothbrush, maybe you've counted the rotations per minute. That would be pretty crazy. And I've definitely driven through some plains or through some open spaces that had these windmills and seen just about how fast those turn. All right, great guesses, everybody. And let's go ahead and take a look at the answer. The answer is the electric toothbrush. So a lot of people may be familiar with the fact that electric toothbrush the motor inside actually rotates very, very quickly, about 7,500 times every single minute. That's incredibly fast, which is why it makes such a good way to clean our teeth. Helicopters, because those blades are so large and so well designed, we really only need those blades to rotate around about 400 to 500 times per minute in order to lift a helicopter off the ground. That's pretty amazing. Less than 10% of the amount of time or rotations per minute of our toothbrush. And then maybe disappointing, but our windmills, right, only rotate about 5 to 20. 20 is the maximum number of rotations per minute that we'd really want to see out of one of these windmills. But if we think about it, that makes a lot of sense, right? They might look kind of small inside this diagram, but those turbine blades, just one blade is longer than a semi-truck. They are incredibly large and incredibly heavy. It would be dangerous and extremely difficult to rotate those massive blades more than 5 to 20 times per minute. What's amazing, though, is there's all sorts of machinery hooked up into these windmills, which can generate more rotations per minute as a result. So even though the blades themselves only rotate 5 to 20 times every minute, they're hooked up to machines that rotate about 7,000 times per minute, because windmills are really the generator, right? So we're not powering the windmill with a motor, even though we can. They're not powered by a motor, right? They're taking the kinetic energy from the wind and turning that rotational or kinetic energy into electricity or power for people to use inside their homes and their cities. So kind of opposite than these two, right? These are machines that rely on a motor to work, whereas this is a machine that actually provides us power. And the wind can be fast or slow, right? But we can actually turn off these windmills if it is too windy. So our friend in Zoom pointed out that the wind can be slow, but the wind can also be incredibly fast, right? So we can actually put the brakes on, basically. We can actually stop these wind turbines from spinning more than 20 RPM, because that would be incredibly dangerous. If they spun much faster than we want them to, that could be very dangerous. They could break off, they could fly thousands of feet and either damage houses or people or cars. That's kind of why we put them in the middle of nowhere in the large open spaces, because that's where the wind is, but also because they're far away from anything that they could damage if something were to go catastrophically wrong. Great points, everybody. You know a lot about windmills. That's pretty amazing. All right, now we said that the electric toothbrush relies on a motor, and that motor is actually very, very powerful. Over 7,000 times every minute, that motor rotates. So here on our show today, we have Paulette, who's gonna take apart or has taken apart one of those toothbrush motors. And she's gonna also show us something really fun you can do with one that you could even get at the dollar store.
All right, hi everybody. Normally I'm here talking about astronomy, but today I'll be talking a little bit about our toothbrush motors. So, as Anna said, we have electric toothbrushes here, and one thing that I've always loved to do ever since I was a kid was to take things apart. That's actually why I ended up going on and getting my degree in physics. So I study motion and astronomy falls into that field as well. But I love, love, love taking things apart. So what I've done here today is I've taken this little dollar store toothbrush and I've taken it apart so that we can see what's happening inside. So let's zoom in a little bit right here. And here we have what's inside of the toothbrush. This is the part that actually cleans your teeth. And so there's a brush on top right here, and it's actually hollow inside of it. And this is what fits right into the center. So up top right here, we have a motor, and then we have a little housing for that motor. So the motor has the plus side and the minus side attached to our battery right here. And when we make a full connection across the board, we can see that our motor makes the top right there rotate, and it's rotating very, very quickly. So you can see not rotating and then rotating very, very quickly for our electric motor. Now we can actually use this motion to do something really cool. We can use this motion to create something that we call a scribble bot. So I'm going to zoom back out right here. And I already made one of my scribble bots right here. This one is, let's see, let's name him Robot 345. Not a very creative name, but here we have him. And we can actually create one of these at home using things that you can find just at the dollar store or things that you might even have around your house. So I made a run to the dollar store yesterday and picked up everything that you see here today. And it turns out that dollar store toothbrushes, the ones that are really inexpensive, are the best toothbrushes to use for this activity. So I have right here a pool noodle. And what I've done is I've taken this pool noodle and I've cut off a really big section of it right here. So I have a green one and I have a red one, but we took that pool noodle and we cut it down. This is a part that I would always suggest to ask for help from an adult. Please don't use scissors or knives or anything like that without adult supervision, but you can take it and cut a little bit of that off and you'll have the little piece of pool noodle that we have right here. Now with this little piece of pool noodle, we can decorate it any way that we want. So I happened to buy some robot stickers when I was at the dollar store because I think robot stickers are really cool. And I love using googly eyes as well. So I have some of those here. I've got some googly eyes. And you can get the ones that stick on by themselves, but I happen to get the ones that don't stick on by themselves, but I got some really fast drying glue that you can get at any craft store. I also actually got it at the dollar store. So we can add some eyes to it. But the point of this robot that we have is to actually have these little markers on it and be able to create a drawing with our little scribble bot. So you can use these little thin markers that you can also get at the dollar store. And I actually just am using some hair ties because that's what I happen to have lying around the house. So you can rubber band as many markers in any colors that you want down here at the bottom. And I'm doing this before I add my pipe cleaner because it just makes it a little bit easier. There we go. The nice thing about using a hair tie is I don't have to go around multiple times. If you have a really big rubber band at home, you can use that, but you'll have to go around multiple times to stick the markers on the bottom. And then you can decorate it with other things that you might have lying around the house. So for example, I happen to have googly eyes on these stickers, and I also happen to have some pipe cleaners because I think pipe cleaners are a lot of fun as well. And you can actually stick these pipe cleaners into the pool noodle, which I really enjoy doing. So here we go. You can give them some arms. Just stick that pipe cleaner in there. There we go. But be careful with pipe cleaners because they do have some sharp edges. So ask for permission before you just start using them. And then you're going to want your Scribblebot to balance. Now I'm leaving the caps on my Scribblebot for now because we don't want to be marking up the table, but I do have a piece of paper here. And we can take the caps off of our markers, just move all of this stuff out of the way right here. And take the caps off of our markers and put them onto our piece of paper. And instead of the automata that we saw yesterday, having to crank them ourselves, we're going to add our electric toothbrush to the top. And that's what is going to allow us to have this drive itself. So we go ahead and put our electric toothbrush into the top right there. Again, make sure that everything is nice and balanced right here. And I am going to go ahead and turn our electric toothbrush on. So when I do that, what do you think is going to happen to our Scribblebot? So if I turn this electric toothbrush on with the motor inside, what do we think is going to happen to our Scribblebot that we have right here? So if I turn that electric toothbrush on and there's a motor inside of it rotating fairly quickly, what is going to happen to our Scribblebot that we have? I have some answers, but I'm waiting for just a couple more. Again, we have our motor right here, and what is going to happen? Some people say that it's going to vibrate, it's going to scribble or move around, it'll jump, it'll move. All right, let's go ahead and turn on our electric toothbrush and see what happens. So he just vibrates across the table and draws a pretty picture for us. And depending on how you aim the markers, the Scribblebot can do circles around, or it can just move across the table like this one. I'm going to keep a close eye on this because I want to make sure that I don't draw here on my table. But here we have our Scribblebot moving its way around. So let me see if I can get it to actually spin. But Anna, do you have any Scribblebots that you've been working on?
Oh, you know I do, Paulette. You know I do. So I have created a couple Scribblebots using some of the same materials. Unfortunately, I don't have any robot stickers, and I agree, robot stickers are super cool. But I did have some pipe cleaners and some pool noodles and some markers and rubber bands laying around, and I'm just getting my last couple tweaks done so that I can balance them before I turn them on. And what I've designed is by using multiple Scribblebots, I've made battle bots here today. So we'll go ahead and turn on our first one, turn on our second one, and we'll see if we can get them off their tracks a little bit. They seem like they're the world's most pacifist battle bots. They don't want to really touch each other here. But like you said, all we need to do is adjust our markers and we can totally change that. So we can get them to kind of move around the table a little bit better, maybe bump into each other, knock each other down. Oh, they're locked up here now. Now it's getting to be a really big fight. Everyone tell me in the comments, who do you think is going to win? Is it going to be red bot or blue bot? Red bot or blue bot? We're kind of jammed up here on a, come on, red bot. There we go. Red bot is here. My money's not on you, but maybe the Facebook world believes in you. But although maybe they're not the best fighting robots, maybe you need to make some modifications, like giving them some sort of weapons or things that they could fight with each other. What they are doing on the paper, though, is scribbling. So they are moving back and forth because that motor inside is vibrating as it rotates around that 7,000 times per second. These guys are wiggling around the paper, taking the ink from the markers with them, and they're creating some fun art down on the paper. We'll add a third BattleBot to the mix. So BlueBot got a lot of votes there, but let's see if BlueBot can hold his own when we toss PurpleBot into the mix. And PurpleBot, there we go. PurpleBot's making a move. They're really all, oh, we're tied up on each other's pipe cleaners, I think is the biggest issue. Well, maybe Scribblebots aren't the best fighting robots, but again, you can tweak these designs and you can make them your own. So if you decide to try this at home, you can always, of course, follow our activity guide that we'll be posting today for this activity. If you make your own Scribblebots, you should show us. So definitely make sure you send us a picture on Facebook or on Instagram so that we can see what you've made. Paulette and I would love to see them and have them join our Scribblebot family because they are so, so cute and so fun. All right, well, let's see. If anyone has any questions about our electric motors episode of Echo Live, go ahead and you can type them in the chat for us. At this time, as always, we would like to thank the sponsors of the Michigan Science Center who allow us to bring these programs to you for free at home. So our sponsors like the Ford Motor Company Fund and Denso allow us to bring these programs to you for free so that you can learn science activities that are easy and fun to try at home. We, of course, hope we'll see you back here tomorrow for another manufacturing episode of Echo Live in honor of National Makers Week. So we've got even more fun programming around for the rest of the week and all the time while you are at home. You can check out the Michigan Science Center's website right down here at the bottom if you're looking for activity guides or experiments that we've done on Echo Live so that you can try them at home. All right, let's see. No questions yet, but people are pretty passionate about PurpleBot here, even though he's kind of hit a roadblock as he's left my coloring sheet down here on the bottom. But let's go ahead and we can take a look. If we turn off our bots, we can take a look at the art they've created. Paulette, did yours make any beautiful art?
It sure did. Actually, I got it so that it was rotating around.
Wow.
Loving this picture that it made.
You chose some very beautiful colors for yours. Mine are a little bit more of like an earth tone type deal, but I got some kind of back and forth, but also some rotational motion. And again, that's because the motor inside the Scribblebot, right, is spinning around in a circle. So even though the resulting motion that we really are looking for is a back and forth to clean our teeth, it is really rotating in a circle, which can kind of help the Scribblebot to rotate in this kind of pattern. Lots of people curious about how fast other kinds of motorized objects could spin. Fans are variable. So I do see that someone asked specifically about fans. And that can depend, right? So there's usually different power levels on a fan, but it's probably still thousands of rotations per minute. So probably pretty quick, just like our electric toothbrush motors, because it has to be in order to move enough air for us to feel cooled off. And just fun fact, fans actually only work when people are in the room. Not to mean they turn off, but that fans are only good for moving air, which makes us feel cool. They don't actually do anything to cool down a room itself. Something I learned recently. Can you add balloons to make the Scribblebots fly? I don't know how many balloons that might take, but I would say it's definitely possible. Maybe if you wanted to take your Scribblebots into the air, make them astronaut bots, please try it. I'd be really interested to see how that goes and what it looks like. It might take a few balloons in order to get enough thrust, but since you won't necessarily be using your toothbrush motor, that's a good chunk of weight that you could remove from your bot, and maybe it would only take you a couple of those helium balloons. Courtney asked Paulette, what do you use to cut your pool noodles?
So I used a bread knife to cut mine because it has that serrated edge and gets through the pool noodle really easily. And the sharper the knife you use, the less likely you are to cut yourself. But again, always ask your parents' permission and help when you're using something like a knife or even a pair of scissors.
Absolutely, absolutely. And using a knife or something like that will give you a nice smooth cut too, as opposed to you probably could just break your pool noodle in half, but you might get kind of a rigid edge, which is okay though. It's just a different kind of style of Scribblebot. All right, so that takes us really to the end of our program. We're a couple minutes over, but thank you everyone so much for joining, and thanks Paulette for teaching us how to make Scribblebots. This was so much fun, and we'll see everyone else back here tomorrow. Have a